Fatigue failure is a critical concern in material science and engineering, particularly for components subjected to cyclic or fluctuating stresses. Unlike static loading failures, fatigue failures can occur at stress levels significantly below a material's ultimate tensile strength, making them particularly insidious. This blog delves into the intricacies of fatigue failure, exploring its causes, mechanisms, recognition methods, and mitigation strategies. Understanding fatigue failure. Fatigue failure refers to the progressive and localized structural damage that occurs when a material is subjected to cyclic loading. Over time, these repeated stresses can initiate cracks that propagate and eventually lead to catastrophic failure. This phenomenon is especially prevalent in materials exposed to fluctuating tensile stresses, such as those found in automotive, aerospace, and structural applications. Causes of fatigue failure. Several factors contribute to the initiation and propagation of fatigue cracks. Improper design. Designs that incorporate sharp corners, notches, or sudden changes in cross-sectional area can lead to stress concentrations, which are prime sites for crack initiation. Material selection. Using materials that are not suited for the specific loading conditions can result in reduced fatigue life. For instance, materials with low fatigue strength or poor resistance to environmental factors may fail prematurely. Manufacturing defects. Flaws introduced during manufacturing, such as inclusions, voids, or surface imperfections, can act as stress concentrators and initiate fatigue cracks. Improper heat treatment. Incorrect heat treatment processes can alter the microstructure of materials, affecting their mechanical properties and fatigue resistance. Surface roughness. Rough surfaces can serve as initiation sites for cracks due to stress concentration at surface asperities. Environmental factors. Exposure to corrosive environments can accelerate fatigue. Failure through mechanisms like corrosion fatigue. Mechanism of fatigue failure. The fatigue failure process typically progresses through 3 stages. Crack initiation. Microcracks form at points of stress concentration, often at the surface or near defects. Crack propagation. With each loading cycle, the crack grows incrementally. The crack path is often perpendicular to the applied stress. Final fracture. Once the crack reaches a critical size, the remaining cross-section cannot support the load, leading to sudden fracture. During crack propagation, features known as beach marks or striations may appear on the fracture surface, indicating the incremental growth of the crack. Recognition of fatigue. Failure. Identifying fatigue failure involves examining the fracture surface, smooth area. The region where the crack initiated and propagated slowly appears smooth and may show beach marks. Rough area. The final fracture area, where rapid failure occurred, appears rougher and may exhibit a cup and cone morphology in ductile materials. The presence of both smooth and rough regions on the fracture surface is indicative of fatigue failure. Mitigation of fatigue failure. To reduce the risk of fatigue failure. Design. Optimization. Avoid sharp corners and sudden changes in cross-section. Use fillets to reduce stress concentrations. Material selection. Choose materials with high fatigue strength and suitable for the operating environment. Surface treatments. Processes like shot peening or surface hardening can improve fatigue resistance by inducing compressive residual stresses. Quality control. Implement rigorous inspection procedures to detect manufacturing defects. Protective coatings. Apply coatings to protect against environmental factors like corrosion. Conclusion. Fatigue. Failure is a complex process influenced by design, material properties, manufacturing quality, and environmental conditions. Understanding the mechanisms and recognizing the signs of fatigue failure are crucial for preventing unexpected failures in engineering components.